Thank you. Ah. Okay, welcome to all the people who have been waiting. I'm not quite sure what went wrong. All right. We're ready. All right, let me do a quick recap on where we are up till now. We've been having class here, but for some reason I wasn't connected to the right stream, I guess. We are looking at section 2.5, second order linear constant coefficient homogeneous ordinary differential equations. And it's easier to write one down than it is to say the title. It's equations of this form: y double prime plus ay prime plus by equals 0. And we're going to learn how to solve all such equations tonight, along with some other things that come up. I've mentioned so far that if you write one of these things down, there's a corresponding polynomial that's called the characteristic polynomial that goes with this ordinary differential equation. It is given by this. You just basically, you copy it. Where there's a double prime, y double prime, you write lambda squared. Where there's a y prime, you write lambda. And where there's no derivative at all, you just have a constant. So that's the characteristic polynomial. And I just haven't got to it yet. I'm just about to try to motivate why this thing should have anything to do with solving that differential equation. So in order to do that, I'm going to cut back to the case where we have a first order linear differential equation, but I want to restrict it to the case we've been looking at here. We're going to have first order instead of second for the beginning here, but it's got to be linear. Well, we got that with this formula, but constant coefficients, that means that thing has got to be just a number, and homogeneous means that right-hand side is going to have to be 0. So let's take such an equation, y prime plus, let's say, ay equals 0. What would its solution look like? Well, you probably actually could guess its solution, but since it's good to review, I'm going to use the formula. We know that the solution here, the general formula, is y equals e to the minus h times antiderivative e to the h r dx plus c, where h is an antiderivative of this coefficient p. That's what we did last time. And we can apply that here as well. So let's see what it would look like if we did that. First of all, we'll have to figure out what h is. It's an antiderivative of that coefficient function, which in this case is just a constant, a dx. So you get ax. You needn't bother with the constant of integration. It's already taken into account there. The solution is y equals e to the minus h, antiderivative e to the plus h, r dx plus c. And now when we go to fill in the blanks, we have minus ax is minus h, e to the h is ax, but r, oh my goodness, that's just a 0, right? The right-hand side of this equation is 0. So this whole antiderivative just drops out. And you end up with e to the minus ax times a constant. So there's the general solution to this one, which is the analog to what we're looking at, except we're going to be looking at second order and this one is first. And you can see, well, you always get an exponential function. And that's it. Once you find it, all possible constant multiples of that is the whole set of solutions. And if you think about it a little bit, you realize that if I took one of these and like this, C1 e to the minus ax, and took another one, C2 e to the minus ax, if I added a couple of those together, I'd get the same kind of function back, right? It would be C1 plus C2, quantity C1 plus C2 times e to the minus ax. And if I took one of these and multiplied it by a constant, like 5, well, then I have 5 times a constant. It's just a constant, e to the minus ax. These things, this is actually, this set of solutions is a vector space. So is a subspace of some vector space, but it is a vector space in its own right. And the same thing will be true for the solutions of this. This is the set of solutions is a vector space that has one function, e to the minus ax, in its basis. This will be a vector space that has two functions in its basis. And in general, if you have an nth order linear ordinary differential equation and the right-hand side is 0, the set of solutions is a vector space with dimension n. So that's pretty useful information. Okay, so the main point, though, about looking at this is we know that for this kind of equation, you should always expect an exponential function. So that would motivate a guess. Maybe we at least have, in some cases, an exponential function that solves this one. Okay, so that's what we're going to do. We're going to take that as a working hypothesis and see what we can come up with. So we're trying to solve y double prime plus ay prime plus by equals 0. And we're going to look for exponential solutions. And that's where that lambda comes in. It's just traditional to use the, instead of a, to call it lambda. And since I would hate to ever break tradition, in math anyway, we will do. Okay, well, let's decide what derivatives look like. The first derivative of e to the lambda x would be, well, e to the ax has the derivative e to the ax, and then you get a chain rule factor of a, right? So this would be lambda e to the lambda x. And the second derivative, well, the same sort of thing would happen. This is just a constant. So when you take the derivative of e to the lambda x, you get lambda e to the lambda x. So we'd have a second factor of lambda out there. And we know what y is. That's e to the lambda x. So plugging it into that equation there, let me call that equation 1. Y double prime is this, lambda squared e to the lambda x plus a, that comes from the equation, times y prime, that's lambda e to the lambda x, plus by, well, y, we're assuming, has the form e to the lambda x equals 0. And you will notice there's an e to the lambda x on every single term. Let's factor that off. We got lambda squared plus a lambda plus b times e to the lambda x equals 0. Now, exponential functions, you know, their graphs look like this, at least if you have a positive number for lambda. They hover along the x-axis, and then right at x equals 0, their intercept is 1, and then they shoot up very rapidly. But the point is, these things never, ever cross the x-axis. And if I made lambda negative, it's pretty much the same thing. It's just you get the mirror image. And of course, I could multiply it by a constant, but that would just stretch or perhaps flip this over, but it's never, ever, ever crosses the x-axis. So the point here is e to the lambda x is never 0. So if this equation is going to have to be equal to 0, then it's going to have to come from the polynomial. And that is that characteristic polynomial that we were talking about. Of equation 1, which is this guy. So if we're going to find a solution of that form, it will be of the form, it will come from setting the characteristic polynomial equal to 0 and solving it. Now, rather than get all tangled up in a bunch of theoretical looking stuff, what I want to do is give you an example at this point, and we'll solve it completely. So y double prime plus y prime minus 12y equals 0. I am going to solve this equation, and it's actually going to go really fast. So what I first do, step number 1, is I write down the characteristic polynomial. Lambda squared plus lambda minus 12, and then I set it equal to 0. And I ask myself the question, can I solve that? Yes, that one looks actually pretty tame. Let's see, 3 and 4 are factors of 12, right? So it's pretty easy to get a difference of 1 that way. So now in this case, it's easy to guess, but if it's not easy to guess, let me just tell you what I do. I write down something I know is not true. One of these two is going to have to be positive, or you wouldn't get a negative there. But then I just take a quick calculation and see what I want. This would be minus 4 lambda minus 3 lambda for the middle term. So I want a positive middle term, so the bigger of these two values needs to be positive. And lambda is minus 3 and 4. We have 2. This is the example of 2 distinct solutions. In other words, 2 solutions that are not equal to each other, and they're real. So where did we?
3 and -4, right?
Yeah, 3 and -4. Oh my goodness, I wrote the negatives down. Thank you. I think you saved me last time on something too. If it keeps going like this, we'll just trade places. Okay, so lambda 1 and 2 are positive 3 and negative 4. And we were starting from an assumption. The assumption was, do we have any solutions of the form e to the lambda x? And so the answer seems to be yes. It looks like y1 equals e to the 3x, and y2 equals e to the minus 4x are solutions. Now that is incredibly good news, because what comes out of the theory of linear differential equations is that the number of solutions, well, first of all, for a homogeneous equation, the solution set is a vector space. And furthermore, its dimension is the same as the order of the equation. So this is a second order equation. We have 2 different solutions. It's got to be a basis, right? So any linear combination of those 2 should be a solution. We should probably check these though. Let's just make sure that this works. I'm going to go for y1 first. That's e to the 3x. If I take y1 prime, I get 3e to the 3x. And y1 double prime, I get 9e to the 3x. And if I plug that into this equation, it's supposed to come out to be 0. So y double prime plus y prime minus 12 minus 12y equals, well, y double prime is right here, 9e to the 3x, plus y prime is plus 3e to the 3x, minus 12 times y, which is e to the 3x. And you can factor the e to the 3x off from all three terms, and the coefficient is 9 plus 3 minus 12. I got this one, Jorge. 0. Make sense? And the reason this works so nice, well, for a couple of reasons. Number one, it's linear. So these things just kind of, you multiply by constants and add stuff up. Number two, the chain rule factors are coming from that coefficient on x up in the exponent. And it turns into a differential equation. And I mean, a quadratic equation. So we've just checked one though. There's one. Let's check the other one. Check y2. Well, y2 is equal to, what did I say, e to the minus 4x. Its first derivative will be minus 4, e to the minus 4x. And its second derivative will be 16, e to the minus 4x. And if you plug these functions in to the original ODE, it is supposed to give you 0. So the original ODE is y double prime plus y prime minus 12y. And y double prime is 16 e to the minus 4x plus y prime minus 4 e to the minus 4x. And minus 12 times the original y, e to the minus 4x. And let's check. 16 minus 4 minus 12, sure enough, is 0. So the general solution is y equals c1 times the first basis function, e to the 3x, plus c2 times the second basis function, e to the minus 4x. There is the solution to the ODE. That paper wants to curl up. So what do you do if you get two distinct roots to the characteristic equation? Well, in this case, we got 3 and minus 4 as the two roots. And you notice they occur here, 3 and minus 4, as the coefficients of x or t or whatever the independent variable is in your general solution. Make sense? Okay, so that's the first case. Second case. Case 2. Now remember, this is all coming from setting the characteristic polynomial equal to 0 and solving. It could be that lambda 1 and is equal to lambda 2, which in that case we'll just call it lambda. So you'd have a repeated real root of the equation, p of lambda equals 0. Okay, now it turns out that the solution in that case is this: y equals c1 e to the lambda x. This much you would guess, right? Because it worked last time. It seems like it should work this time. But you can just plug in the other, you can't just plug in, by the way, these are called eigenvalues of the equation. You can't just plug in the other eigenvalue because we already, the two of them are the same. So it wouldn't give us a different function. It turns out though, that there's a really easy trick to get another one. And that is e to the lambda x is one solution and x e to the lambda x turns out to be another solution. So again, I could say some things theoretically, but I'm not sure that it would be nearly as helpful as just doing one of these. So suppose we had y double prime minus 8y prime plus 16y equals 0. And I want to solve this differential equation. Well, when I write down my characteristic polynomial, I'll get lambda squared minus 8 lambda plus 16 equals 0. And 16 is a perfect square. So it looks like lambda minus 4 would be a factor. And in fact, it is. It's both factors. If you square that, you get lambda squared. This times this doubled, minus 8 lambda, minus 4 squared is plus 16. So that's the factorization. And we have the case of a repeated real root, 4 and 4, for our eigenvalues. And I should write this down. Okay, so the general solution is y equals c1 e to the 4x plus c2x e to the 4x, and this should work. Now, this one probably most people would just believe me, right? Because I mean, we just did it with we just did this trick before where you take an eigenvalue as a coefficient on the independent variable in e to the ax or at or whatever. So that seems like it should work. Let's check this other one though and see, because that I just presented it as a wild guess. I said, gee, I think this would work. Well, it wasn't a wild guess. But I didn't provide any motivation. So let's at least check it and see what happens. Okay, if I take the, oh, I don't want to say lambda here. We've got a particular lambda in mind. It's 4. So if I take the derivative of x e to the 4x, well, I got to use a product rule because I have two functions multiplied together. When I take the derivative of x, I get 1. So 1 e to the 4x. And then if I take the derivative of e to the 4x, I get 4 e to the 4x. And the second derivative will be even messier. Okay, taking the derivative of e to the 4x, I get 4 e to the 4x. And now I got to use the product rule for this second one, plus derivative of 4x is 4 e to the 4x, plus, okay, now I'm going to preserve the 4x, but take the derivative of e to the 4x, so that's 4 e to the 4x, but I already had a 4, 16x e to the 4x. And finally, or did I do it all? That's it, plus 0. Okay, so let's plug it into the equation and see if it works. And the differential equation we're trying to solve is right up here. Y double prime minus 8y prime plus 16y equals, Okay, y double prime is this mess. You know, there's an e to the 4x on everything. So how about if we sort of factor that off? I've got 4 e to the 4x plus another 4 e to the 4x plus 16x e to the 4x. That's the coefficient on e to the 4x for y double prime. And I'm going to have another set of parentheses here. Minus 8 times, okay, y prime is this one. It'd be 1 plus 4x e to the 4x. And plus 16. And it's 16 times x e to the 4x. And we'll just write e to the 4x off to the side, factored out. And you set that equal to 0. Okay, so what do we have here? We have 8 plus 16x minus 8 minus 32x plus 16x. And I believe that adds up to 0, right? 8 minus 8 is 0. 16 and 16 make 32 minus 32. Sure enough, that is just 0. Oh, and I ignored my e to the 4x. But it's e to the 4x times 0, which is 0. So it worked. So that's case 2. And we're less than an hour into this lecture, and we've got 2 of the 3 cases done. Whew. 10 more minutes, we'll be out of here. Well, it turns out that case 3 is a little bit more complicated. But we might get out early. I hope so, that would be nice. All right, does anyone have a question about this one? If this thing has a repeated real root, then e to the lambda x and x e to the lambda x are the basis functions.
So is it always going to be an exponential function?
No. And the non-exponentials will come up in case 3. But in case 1 and case 2, the answer to your question is yes. Now, I should maybe modify that a little bit, because it depends on what you mean by, is it going to be an exponential function? Is this an exponential function? No, technically not. But it involves an exponential function, right? It's an exponential times a polynomial.
Okay.
And it turns out that at least indirectly, exponentials are involved in all 3 cases. But they kind of, you can get a case where it's pure trig functions, but it turns out they're related to exponentials, and that's where they come from. So, case 3. Suppose we're solving this. I'm just writing this down for reference because it was not on this page. Same thing as before. We switch to the characteristic polynomial, set it equal to 0. And case 3 would be this. Lambda equals, and I'll just tell you, this might look a little strange. I'm following the notation in Kraitzik's book, Advanced Engineering Mathematics, and he calls this alpha plus or minus I beta. So alpha and beta are real numbers. So for instance, this could be like 3 plus or minus 4i or something like that. A complex conjugate pair now, if we just follow our trick in case 1, I mean, after all, these things are different, right? One of them is going to be alpha plus I beta, and the other one is alpha minus I beta. The beta can't be 0 because if it were 0, this would not be a complex conjugate pair. It would bounce us back to case 2. So these are really different solutions. And therefore, you saw the algebra work out. If two solutions can be found immediately, I'm going to call these Z. Z1 equals E to the alpha plus I beta X, and Z2 is E to the alpha minus I beta X. And if you're willing to have functions that involve complex numbers, well, we're done. If you stick these back in the original ODE, you will see that the algebra works out every time and you get 0. Unfortunately, however, you got these complex numbers involved. Potentially, we could be getting complex numbers out of our functions. And you know, if you're trying to design a circuit and now you got these complex valued functions, what does that mean? Ooh, you know, that's a little disturbing. So we got to go to a 4-dimensional space to figure out what our circuit is going to do. Well, no. As you all know, the circuits do behave in ways that we can easily measure and predict even in ordinary 3 space along with time. So we would like to simplify this. Now, what we need to do that is this. E to the I theta is equal to cosine theta plus I sine theta. And this even has a name, which I've forgotten. Oh yeah, Euler's formula. I made a joke about that one time in a class, and it didn't go over well. So now I suppose it's a meta joke. What I said was, now physicists call this Euler's formula, but mathematicians just call it obvious. I had a lot of physics students. They took it as an insult. So sorry. Still sorry to all those people all those years ago. I wasn't trying to be offensive. Well, it's obvious if you've seen it 1,000 times before, right? Now, why on earth should that be? Well, here is why. E to the x is equal to 1, no, wait a minute, x. One plus x to the 1 over 1 plus x squared over 2 times 1 plus x cubed over 3 times 2 times 1 plus x to the 4 over 4 times 3 times 2 times 1 plus, and unfortunately, if I write out the whole thing, this class will never, ever end because this goes on forever. It's an infinite series. Now, this is just an aside. It's not part of the derivation, but this is worth noticing. What would happen if you took the derivative of e to the x? Well, every one of these terms is just a polynomial term. We know how to take the derivative of that. Derivative of 1 is 0. The derivative of x to the 1 is 1x to the 0 over 1. Derivative of x squared is 2x over 2 times 1. Derivative of x cubed is 3x squared over 3 times 2 times 1. Derivative of x to the fourth is 4x cubed over 4 times 3 times 2 times 1, and we hope we can figure out the pattern from that many. If you do a little simplification, well, this one just goes away. 1 over 1, x to the 0, that's 1, so you get 1. Here, the 2's cancel out, and you've got x to the 1 over 1. Here, the 3's cancel out, and you got x squared over 2 times 1. Here, the 4's cancel out, and you got x cubed over 3 times 2 times 1. And this goes on just like this forever. And if you look at this line here and this line here, you will come to the conclusion, oh my gosh, we got the same series back that we started from. Huh. So when your Calculus 1 teacher said the derivative of this function is itself, they were not lying. And there are certain properties of common functions in the power, this is called a power series formula, in the power series form that just become, once you have the series, I'm not saying the series is easy to come up with, but once you have the series, some of these identities are really are obvious. The derivative of e to the x is itself, and you just compute it and see what happens. It worked. It's amazing. Now here is another thing that we should know about. Let's take some powers of the number I. By I mean just what you're thinking already probably. It's square root of -1. So I to the 0, I to the 1, I squared, I cubed. Let's do a few more. Okay, so we'll compute a bunch of these. And by compute, I mean I want to simplify them as much as I can. Now, any non-zero number raised to the 0 power is 1. I don't know how you're going to make I to the 1 any simpler. That's just I, right? Now, I squared is, yep. Look right above. I is root -1, so I squared is close. -1, yeah. So now I'm inferring you did not do this in high school, right? Or if you did, you don't remember. Yeah, okay. All right, now I cubed, that's I squared times I, but I squared is -1. So I cubed is -I. I to the 4th, well, that would be I squared squared. I squared is -1, -1 squared is +1. Okay, I to the 5th. Well, that would be I to the 4th times I, but I to the 4th is 1. So that's just back to I. I to the 6th, well, you take out 4 of those factors. I to the 4th, that's 1 times I squared. I squared is -1, so -1. I to the 7th, that's I to the 4 plus 3. The I to the 4 part is just 1. I cubed is -I. Hey, look, 1I, -1 -I, 1I, -1 -I. Can anybody guess what the next 8 terms in this sequence are going to be? It's just going to be that all over again. So this, this sequence right here, 1I, -1 -I, that just repeats forever and ever as you look at the powers of I. And now I want to consider this function, e to the I theta. Probably wouldn't hurt if I got it up on the screen. Okay, e to the I theta. Well, we said earlier, way back here, e to the x is 1 plus x to the 1 over 1, x to the 2 over 2 times 1, etc. By the way, this 4 times 3 times 2 times 1, that's 4 factorial, right? Is that familiar to you all? So maybe I should just write this down because it makes crummy notes if I just say it. 4 factorial means 4 times 3 times 2 times 1, etc. N factorial is n times n minus 1 times ... times 2 times 1. And 0 factorial, by the way, is simply defined to be 1. Okay, so now I'm ready for e to the I theta, but I think I'm going to change pages here because it's going to take some work. Maybe I'll turn the paper sideways so that way. No, it won't work on a camera. Okay, e to the x, for review, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial, and that pattern just goes on forever. It never stops. From calculus 2, the sine of x turns out to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, etc., x to the 8th over 8 factorial. And this, this just pattern goes on. You'll notice that all of the powers on x are odd. 1, 3, 5, 7, oh, I said 8. Silly me. That was definitely not true. 1, 3, 5, 7, 9, etc. The power on x is always matched by the factorial down below. So if it's x to the n up here, then it's going to be n factorial down below. So that's the sign. The cosine looks very similar, except it works with even powers. X to the 0 over 0 factorial, which is 1. That whole term is 1. Minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus minus, etc. So it does the same thing as the sine does, or similar pattern anyway, but it works just with the even powers, 0, 2, 4, 6, 8, etc. But you're getting this alternating sign, plus, minus, plus, minus, plus, minus. And the exponent is always reflected by the size of the factorial. 6th power, 6 factorial, 4th power, 4 factorial, etc. Okay, we are now ready. What is e to the I theta? Well, I'm going to write out probably about 8 terms, which will be tedious, but it turns out it's going to split nicely into 2 different series. And I'd like those 2 series to have at least 4 terms so you can see the pattern. So that's why I'm doing so much of this. Okay, the rule is right here. I'm just replacing x by I times theta. So I have 1 plus I theta, which I'll put in parentheses to emphasize it just came from 1 term of the series, plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial. And it's going to keep going like this The general term looks like this: I theta to the nth power divided by n factorial, but that is not the end. It keeps going forever. And now we're going to do this trick right here of simplifying the powers of I. Whoops, get that up here. Simplify the powers of I to make this thing look a little friendlier. E to the I theta equals, well, one's pretty simple. I theta can't be improved on. Plus, okay, now, when you square I squared is -1. So I've already written something I didn't want to. And you've been wondering, perhaps, you know, when he posts his solutions online, they don't have a bunch of scratch outs. When he lectures, they always do. It's amazing, isn't it? You too can appear precise and intelligent. It takes $1. Might even be 99 cents. So, all right. So I squared is -1. Theta squared over 2 factorial. Now I cubed. Well, we computed that, right? I cubed is the same as -I. Why? Because I squared is -1. So minus theta cubed over 3 factorial. And hopefully after we do enough of these, the pattern will be really kind of jump right out. All right, now I to the 4th, that's just 1. It's I squared is -1. So you got -1 squared, which is +1. 1 theta to the 4th over 4 factorial. The next one, well, it's going to be I theta to the 5th. All right. Well, I to the 5th, that's I to the 4th, or 1 times I. So just plain I. Theta to the 5th over 5 factorial. And let me see. Maybe I should do 2 more. All right. Well, what happens when I get to the 6th power? I'll have I to the 6th power. I to the 4th is 1. And then I squared is -1. And whoops, why didn't I just call that minus? I've got my secret open. Thing is, you got to go back and remember after your eyes. Is there a question?
Are we missing an I on the 3 factorial?
Oh, probably. Yes, that's -I. That's a 1. That's an I. This is a -1, but the whiteout's still wet. And then -I, theta to the 7th over 7 factorial. And it doesn't stop there. It keeps going. It's plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, etc. Like that. Okay, now I'm gonna rearrange these, pull out the real terms, the ones that don't have any I. 1, the theta squared term, the theta to the 4th term, the theta to the 6th term. So e to the I theta equals 1 plus, whoops, minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 5th over 5 factorial, and it keeps going like that, plus, minus, etc. Group those together, plus we've got another whole series here. And now our I terms are these, but I'm just going to factor the I out of them. So I don't have to write that every time. I times theta, I've just got theta. The next one is minus I, theta cubed over 3 factorial. So minus theta cubed over 3 factorial plus, where's our fifth order term? I, which is factored off, theta to the fifth over 5 factorial. And at this point, you probably guess. Theta to the 1 over 1 factorial minus theta cubed over 3 factorial plus theta 5 over 5 factorial minus theta to the 7th over 7 factorial. And it likewise continues on as an alternating series forever and ever. However, see this? And I should work my magic here. Oh, except I obliterated the 1. 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. That sure looks familiar. X to the 1 minus x cubed over 3 factorial plus x to the 5 over 5 factorial. Same series exactly, except I got x's here and I got thetas here. So this is sine theta, wrong. I'm doing my very level best to write this formula incorrectly. Cosine theta here, that's a 1 plus I sine theta. Okay, now we were doing this because we were trying to solve differential equations, remember? So we got to this case, case 3, when we're trying to solve y double prime plus ay prime plus by equals 0. We said, what if you had a complex conjugate pair for the roots of the characteristic equation, alpha plus or minus I beta? And I said, you know, you could just do exactly what you did with with case 1, it's just with complex numbers. E to the alpha plus I beta times x, call that Z1, and Z2, you call that E to the alpha minus I beta times x, but now you do a little bit of algebra. This is, well, if you had like 2 to the 4 plus 7, it'd be 2 to the 4 times 2 to the 7, right? You can split those two things up with the same base. So this is e to the alpha x, that's alpha times x as the exponent on e, times e to the I beta x. And this one, likewise, is e to the alpha x times e to the minus I beta x. But we can use Euler's formula. So Z1 is equal to e to the alpha x times the quantity. The e to the I theta is cosine theta, in this case beta x, plus I sine theta, beta x. Z2 is e to the alpha x cosine beta x minus I sine beta x. And the reason for that is that the sine is an odd function. Sine of minus x equals minus sine of x. So if you put a minus minus beta x into the sign. You can just pull the minus sign through. Well, behold, if we added z1 and z2 together, then these complex terms would add out to 0, right? You'd have e to the alpha x cosine beta x plus e to the alpha x cosine beta x. That would be 2 times e to the alpha x cosine beta x. And then if you divided that sum by 2, you'd have just plain old e to the alpha x cosine beta x. Likewise, you could take the difference and divide by 2. So in that case, cosine beta x minus cosine beta x, that will add up to 0. And you'll have I sine beta x minus a minus I sine beta x. You'd have 2i e to the alpha x cosine beta x. And now instead of dividing by 2, I'm going to divide by 2i. And so I get 2 real basis functions, e to the alpha x cosine beta x and e to the alpha x. Whoops, what did I do here? Something stupid. This is sine. E to the alpha x sine beta x. And this we're going to call y1, and this we're going to call y2. Those are our 2 basis functions. So the general solution, the general real solution of the original ordinary differential equation is this. Just any constant times y1 plus any constant times y2. If you clean that all up, it looks like this. Y equals e to the alpha x times the quantity a cosine omega x plus b sine omega x. And sometimes, a lot of times, people want to know, whoa, how come you're doing A and B? Up to now, you've always made your constants C1 and C2. It's to make this look different, and it helps with memory. So, you got to remember these 3 formulas for case 1, 2, and 3. So, actually, I'm following Kreyszig is what I'm doing. But I found that it was helpful. I remember the formulas without conflating them when I did it this way. So let's do an example. That might be handy. I better pause for just a minute though. Okay, so let's take this example for case 3. Y double prime, it's got to start that way. I worked out a couple ahead of time, so minus 6 y prime plus 36 y equals 0. Second order linear, ordinary differential equations with constant coefficients and 0 on the right-hand side. All right, when I want to solve an equation like this, the first thing I do is write down my characteristic polynomial, set it equal to 0 to form an equation, and solve that. Well, at first it looks hopeful, 6 and 36. Oh, 6 squared is 36. I ought to be able to do this somehow. You can't. So then you go to the quadratic formula. Lambda equals negative b, so that's 6 plus or minus the square root of B squared 36 minus 4 times A times C all over 2 times A, which is 2. And this is actually probably worthy of a calculator. Huh? Well, 1 times 36 minus 4 times 36 is negative 3 times 36. 108. That doesn't look familiar. Oh, minus 4. Oh, minus. What's that?
36 minus 144.
Yeah, but it's supposed to be a perfect square because I cooked it up so that it would be. What did I do wrong? Oh, this says Yep. Copied the problem wrong. Okay, let's try again. But it's still copied wrong. Minus 4 AC. These have got to add rather than subtract. Let's try another one. I made up 2. Hopefully this one works. It's not that the equation I'm getting there is unsolvable, but I want it to be nice. Okay, this is supposed to work. Lambda squared minus 4 lambda plus 53 equals 0. Lambda equals negative b is 4 plus or minus the square root of b squared 16 minus 4 times a times c 3 all over 2 times a. Okay, 16 minus 4 times 53 minus 196. Oh, good. Because 196 is 14 squared. So this is 4 plus or minus 14i all over 2. So it's 2 plus or minus 7i. Therefore, the general solution to the homogeneous equation is this. E, you pick off, this is the alpha part right here. So alpha is 2 and beta is 7. E to the 2x times some constant cosine 7x plus any other constant sine of 7x.
So omega is beta?
I'm sorry, I didn't hear.
Omega is beta. You use omega last.
Oh, okay. No, I don't want to change it
Okay.
because we use beta in other places and I don't want to tangle up. Omega traditionally is often used in when you have either a vibration or an electrical signal that has a constant frequency. The omega will indicate the frequency. It's the coefficient inside of here.
So that's Y sub 1 or Y sub G?
Y sub G for general.
Okay.
You can just say Y, you know, it's fine here. Now, if you've done some of this stuff, I mean, let's just make one up here. If I turn my calculator, you know, to the proper mode, I would like this in radian mode so that things look familiar to me, at least. If you compute one of these sinusoids, by that I mean a linear combination of sine and cosine, they have kind of predictable shapes. Well, they're exactly predictable, but I mean, without even knowing the constants, you can guess in general. Say if I take 3 sine of 2x minus 5 sine, rather cosine of 2x, and graph it. Oh, I should have increased my. You get what people call a sinusoid. It's a simple transformation of sine or cosine. Now, this maybe doesn't look so familiar, but what if we came up with a case where that were negative? Then, and we can do it with the one that we have here. I'm going to go to insert. And then multiply this by an exponential function. I don't want it to go too fast. Let's try this, minus 0.1x. See what that does. Now, imagine we were describing a mass spring system, but you do have some frictional force. So you pull the weight down, let it go, and it starts to oscillate, right? But due to the frictional forces, the amplitude decays. Or you have probably even heard this. We all hate it when we do, but if you're in a auditorium, someone gets the mic too close to a speaker, you know, you get this, and they say, oh, or they shut it off or something like that. Well, there's some damping in that circuit. The capacitors are doing it. And that horrible noise slowly dies down, right? So, or you don't see it so much anymore now, but back when I was like in high school, you'd see a lot of these big boat cars. I mean, the things are just massive. And they didn't have especially great quality dampeners on the spring systems. And so when they go down the road, they hit a bump. If it was worn out, the shock absorbers were out. The car would kind of, the front end or the back end or both, be going up and down. But if you watched it as it goes down the road, it starts real big and then sort of levels out after a while. Because it does have some frictional forces in there, thank goodness. And now, of course, it is just possible that maybe something like this, if you think of your spring displacement as up and down, then right when it gets down to the bottom, every time exactly at the bottom, you bump it. And you bump it enough that it more than counteracts the amount of energy that's absorbed by the frictional forces. Well, then you have one of these. You take out the minus sign. And now it starts relatively small. And a lot of people have seen like this, there's a old film of, I think it was the Tacoma Narrows Bridge that blew apart in some wind. And that's exactly what happened. The natural frequency of the oscillation in the bridge happened to match the forces that were being applied by the wind at that velocity. And the amplitude just got bigger and bigger until the system physically broke down. And of course, that can happen with electronic circuits too, right? You have a signal, an unwanted signal, and the amplitude goes bigger and bigger until it fries the circuit. So can that happen? Oh yeah. Yeah.
Kind of like in World War I, they were marching on bridges, and because they were marching in sea, like it would gradually break the bridges down.
Yes. Yeah, absolutely. And but until people started building mechanical or electrical systems where they could observe this, it didn't occur to them. So yeah, your squad of soldiers falls into the river 250 feet below, doesn't help you win the battle. But I hope you all will avoid forever being in any armed conflict, whether between states or simply angry people out on the street. It's not anything to enjoy. Okay, I have now told you all three cases. I've given you the secret sauce for I'm looking for my, I'm looking for this paper that's looking at me. I just want to make sure I've covered all this stuff.
I have a question.
Yeah.
In the book, it states it as lambda 1 is equal to negative 1/2 A plus I omega.
Yeah, and you'll notice that I did not state mine in terms of A at all.
Okay. Okay.
If you wish to use the formula that's in the book, by all means. What I do is I write down the characteristic polynomial and set it equal to 0, solve that equation, and then the two numbers I need are sitting right there.
So it's essentially the same formula just written for A.
Yes, yes. So minus A over 2, is it?
Yep.
Is equal to the alpha that I have. But they're consistent. And the reason I don't usually muck around with it is because I think the easiest way to get the omega is to solve the quadratic equation. I think there might be a formula in the book for the.
Yeah, it just shows the derivation.
Yeah. But the easiest way to get the second one of those, the omega, is to solve the quadratic equation by my way of thinking. That's not to say you couldn't come up with a formula for it. And by the way, there's some people who are just unbelievable memorizers, and they will look up a formula like that and say, well, why should I bother solving all these quadratic equations when there's just a formula that I can easily remember? Yeah. Okay, do it. I don't enjoy memorizing, so I usually find ways of deriving what I need quickly. Unless I have to memorize, something you can't avoid. Okay, I think, one last thing. You will see this, and I'm actually supposed to tell you. I'm just making up a differential equation. Now this could be equal to anything, but we can make it a zero. You will see this sometimes written this way. D squared well, no, the y shouldn't be there. The y should be here. And this is a differential operator. And then people will sometimes say, well, define the L to be the differential operator, d squared plus 3d minus 5. It turns out that this thing is a linear operator. Just like the linear operators that we talked about when we were doing linear algebra. So in other words, if you have L of C1y1 plus C2y2, that's the same as C1L of y1 plus C2L of y2, where L is this differential operator. If someone writes one of these things, d squared plus 3d minus 5, and then I think usually they put these in parentheses, and sometimes they'll use square brackets for this. It's just a notation, but if you've never seen it before, it can be kind of shocking. You think, whoa, what's that? It means this: y double prime plus 3y prime minus 5y. That's it. So you can wax eloquent for a few pages on linear differential operators. And in fact, I did on the notes that I hand out. And, if you take a course later where someone actually is working with these things, then it would be nice if you had at least seen them. But I don't usually emphasize them in lecture because they don't really add anything to the equations that we can solve. It's just a notation for writing the left-hand side of the equation. So when you're looking through the notes, and I do hope you look through them, the full notes, there is a section in here on linear differential operators. If you don't really care to read it, you probably skip it. If you know this much, you know what you need to. Okay, well, that's it. So unless there are some questions, we can adjourn.
Is there an assignment for Thursday this week?
Not to be picked up on Thursday. I will post an assignment, and I will post some, I actually don't remember if I've posted these printed notes yet or not, but if I haven't, I will.
Okay.
All right, have a good evening.